Okay, so this section is what we're going to start talking about when it comes to um, looking at um, area under a curve. So we look at area under the curve and we call it something special in calculus, and we call it what's called a definite. A definite integral is found by taking an antiderivative, just like we've done in the past sections, but actually evaluating it from a certain endpoint. So from a, two values of x, so that it's not just arbitrary, but we're actually finding area under the curve. And area under the curve relates a lot to finding different things about, coastlines, depth of a pond. There you'll see a lot of different applications to this. But what I'm going to do, so let's just be clear about finding area under the curve. There's exact area under the curve, which is found when you have an equation similar to this. Okay. And then there's approximate area under the curve when you have something like a table of values. Okay. And so these area approximation methods are used when we cannot find the actual equation to represent them. Okay. So, but for the sake of simplicity, so that you guys can see exactly how to calculate the different approximation methods, I'm using a specific example, a specific equation, and a specific interval to show you how those intervals change things. Okay, so, or how the approximation method changes. Okay, and in the end, we will find what we normally do with actual equations, which I'm going to find the exact area under it. Okay, so you will never use an approximation method for actual equation because you'll be able to find the exact value. And why would you find an approximation? All right, so we have our first approximation method, which is called LRAM. It is called the left-hand endpoint rectangular approximation method. So left Riemann sum is another way of putting it. Just so that you know. And so what we're going to do essentially is we're going to find a bunch of rectangles and a bunch of areas, and then we're going to add them all up. So what you need to know about LRAM is that the left corner of every rectangle that you're going to do is going to touch the graph. So I'm going between 0 and 2, and I need to separate this into 4 rectangles, which is real easy, right? Like I was able to really easily separate that out into 4 areas. And then what I want is I want the left corner of my rectangle touch, which my first rectangle is just along the x-axis. And then I go up, then I go up, then I go up. Ooh, really bad. Like when I find the area of those 4 rectangles and say that that's the same thing as this entire area under the curve, that's terrible. That's a really bad approximation. Okay, we're going to do it anyways. So I'm going to find the area of the first rectangle, which is 0. So we'll start off with a rectangle that actually exists. So the area of my my first rectangle is going to look like my 1/2. So my base is 1/2. So 1/2, and then my height, this corner right here, is found by plugging 1/2 into my equation. So sometimes I'm given my y value or my height, and sometimes I actually have to find it, which in this case, because I'm given an equation, I have to actually find it. Normally it's given to you because we only do this with table of values. So that comes from 1/2 and squared. So then when I multiply this out, I get 1/8. Rectangle 2 is found by 1/2. The height is plugging in x equals 1 into my equation up here. So then I get 1/2, and then 1/2 times 3 halves plugged into my equation is 3 halves squared, and so I get 9/8. So then I add 1/8 plus 1/2 plus 9/8 together, and I get 1/8 plus 4/8 plus 9/8, which gives me 14/8, which is the same thing as 7. Okay, and that is LRAM. Left corner of the rectangle touches the graph. Every single time you are given an LRAM question or any of these approximation method questions, I want you guys to actually draw a graph. Draw a quick sketch, even if it's not accurate, because otherwise you will mess up your corners. Okay. Until you get like big brained. Okay, and then you can do it in your head. But right now, we're all going to do it by drawing it out. Okay. And even though I've done this for years, I still draw out my rectangle. It's primarily because arithmetic. Okay, so now I'm going to draw again. It's the same subintervals, so I'm going, and now my issue is obviously is that I'm an over approximation here. So this one was clearly an under approximation because all the rectangles lie below the graph. If there's a mixture, so like this one is clearly over approximation, but if there's a mixture of above the graph and below the graph, you can't tell. So over approximation. So I have 1, 2, 3, and 4. So now I have still 1/2. And then it's this height again is found by plugging 1/2 into my equation up here. So 1/2 squared. So then I get 1/8, then 1/2 times 1 squared. So I get 1/2, and then 1/2 times 3 halves squared, and I get 9/8. And then I get 1/2 times 2 squared, and I'm going to get 2. And again, I'm going to add all these areas together. So 1/8 plus 1/2 plus 9/8 plus 2 is 1/8 plus 4/8 plus 9/8 plus 16/8. So then I get a total of 30/8, which is the same thing as 4. So the exact area actually under this curve is somewhere between 15/4 and 7/4. Okay. That's another approximation method. This is right Riemann sum or right rectangular approximation method. Then there's midpoint. Midpoint will be a lot easier when I give you guys a table of values, and it's really kind of annoying when I don't. So what I actually mean is that the midpoint of my rectangle touches the graph, or MRAM. And in this case, I'm splitting up my heights of my rectangles. But when you guys are given a table of values, it's going to be really clear. Like you're going to have one table of value and another table of value and another table of value, and the MRAM value was in the middle. So you don't need to find, you just need to use the table of values when you use MRAM. Don't try to split up the interval, okay? Or do what we're doing here, which is we're splitting the rectangles. I don't need you guys to split the rectangles. The rectangles are just going to be wider when you look at a table of values. Okay, so that means that my 1/4 and my 3/4 and my 5/4 and my 7/4 is actually what's going to go into my equation to figure out what my height is. So my bases are all still 1/2, but now it's 1/4 squared and 3/4 squared and 5/4 squared and 7/4 squared. So then when I multiply this out, I get 1/32, 9/32, 25/32, and 49 over 32. And then when I add them all together, 1 over 32, 9 over 32, 25 over 32, and 49 over 32, I'm going to get 84 over 32, which reduces to 21 over 8. So this approximation method is actually better than a LRAM or an RRAM. So MRAM is better. As you'll see, I'm getting smaller above the graph and smaller areas that are empty below the graph, and so we're getting closer to what the exact area is. Okay, so now there's trapezoidal rule. If by some chance you had found LRAM and RRAM already, and I asked you to find trapezoidal rule, you could find the average. You could add the LRAM and the RRAM together, divide it by 2, and get trapezoidal rule. Now, what do you think trapezoidal rule is? Areas of trapezoid. So there's this, like, you know, awesome formula, right? Like, you know, but who wants to memorize stuff like that? What do we know? Area of trapezoid. 1/2 B1 plus B2 times height. Okay. So we're going to use that. So now what I'm going to do is I'm going to draw my trapezoids, which my first trapezoid is actually okay. So now my height of my trapezoid, my height, so I'm like looking at it like weird, you know, and so I'm like turning my head and my heights are along the x-axis. So my heights are actually all 1/2. So my area of my first trapezoid is actually going to be 1/2. 0 is the first base, and the first height is 1/2 square, and then times the height, which is 1/2. So 1/2 B1 plus B2 times the height. Next one, 1/2 squared plus 1 squared times 1/2. 1/2 B1, which is 1 squared plus 3 halves squared times 1/2. And you're going to be like, where are you getting all these numbers from? 3 halves squared plus 2 squared times 1/2. My bases are actually running vertical. So these are my bases here. And then my heights are along the x-axis. So then when I do this and I multiply this out, I'm going to get 1/16, 5/16, 13/16, and 25/16. So I'm going to add all this together, 1/16, 5/16, 13 over 16, and 25 over 16. And then I'm going to get 11 over 4. And what I told you before is that, you know, I could have done this by finding the exact. Okay, so here's how we find the exact, and then we'll do this in the next section. But to find the exact, we're going to take the antiderivative of x squared dx, and we're going from my interval, which is from 0 to 2. And so we find our antiderivative first. So my antiderivative, right, is 1/3 x cubed. And then I'm going to evaluate this from 0 to 2. What that means is I take my top value, which is 2, and I cubed it, subtracted my bottom value plugged in, which is 0. It is always subtraction between, and this is evaluating a definite integral, which represents the exact area under any curve that's given. So this is the exact same thing as 8/3. And obviously you can look to see which approximation method actually was better or worse in trying to get the exact value. Okay, so what I would do is, you probably spent a lot of time writing this down, so I would go back real quick and see if you need to look to see where some of the numbers came from, and make sure that you truly understand what's going on. And if you don't, to go back and rewatch that part of the video. And then let me know if you guys have any questions.